Okay, so let us now start the next class in linear vector space. So, in our from the last class we can understand partially what is we were discussing something about linear functional. And we also give one example of linear functional which was a dot product, and we mentioned that we will give another example which is not necessarily a dot product kind of things, it will be different kind, but that can also be considered as a linear functional. So, the next example 2 is the trace of a matrix. My rule is trace of a matrix. So, what is the trace of a matrix? Say a 2 by 2 matrix can be represented as A11, A12, A22, A21, A22. This is the 2 by 2 matrix, the elements I can write in this way. So, now the trace, if I apply the trace operation over these things, then what essentially we are doing? We just add the diagonal elements here. So, that means outcome is A11 plus A22. This is just a number, this is number and number, two numbers I am going to add. When I add two numbers A1 and A2, I can have a scalar. So, I am adding two numbers and as a result I am having a scalar. So, trace of a matrix is a operation that I operate over A, and as a result I am having a scalar. So, one thing also you should note that A, these things A which is a 2 by 2 matrix can also form the vector space. That means in the vector space V, I can have the elements A, B, all 2 by 2 matrices. For example, they are forming the elements, they are the elements of a vector space. So, now what I am doing that I try to operate this trace function or trace rule over that, and when I operate we find that I am getting a scalar. So, my first condition is valid. The first condition of linear functional is that linear functional is something which I can operate over the vector element, where the vector element here is A, in such a way that it is giving you the scalar. So, now I will try to find out what is going on when I try to apply that in A plus B. So, trace A plus B, what will be the result? So, my A is A11, A12, A21, A22, which is A, and I am adding this as A, another vector B11, B12, B21, B22. A plus B is element of the vector space, and I am adding to, I am getting a new vector element, I called it C, where C is just the addition. If I do the addition, you can readily find that the addition is A11 plus B11 plus some terms here. I am not going to write this, I am just interested only the diagonal terms for the time being. So, it is A22 plus B22, this structure, the structure wise it will be something like this. So, now if I make a trace over that, I will have what value? So, if I write this here, so I will have A11 plus B11 plus A22 plus B22, which is essentially A11 plus A22 plus B11 plus B B22. A11 plus A22 and B11 plus B22 is nothing but trace of A individually plus trace of B. So, my first rule is satisfied. Function over A plus B is equal to function A plus function B. This function is a trace function, and both the cases it is giving the scalar things. The rule 1 is satisfied. Now, what about the rule 2? Rule 2 gives me that just write to recall, the rule 2 is A, if I over a vector, then it will be F, these things. If I try to do the same thing with this, so trace of some multiplication A with A is nothing but A trace of A. I am not doing meticulously, I suggest you to do and check whether this is valid or not. I believe it will going to valid, and if it is there, then we will have another example of linear functional. So, linear functional is, I give you the two examples where the essential rule is that if you apply that over a vector, the vector will transform to a scalar quantity, and following these two independent rules, that if we operate A plus B and I will get individual things, and a scalar multiplication can come outside. So, now I can understand what is linear functional mean. Now, after understanding the linear functional, now let me go back to our original problem, which is dual space. And by definition, in the last class we mentioned that a dual space is a collection of all linear functionals. So, if a vector space is defined with a vector, say alpha, beta and so on, then a vector space is defined like this. So, the corresponding dual space will be containing some other vectors like this. Now, we call these vectors, and this case they are also forming a vector space. One can prove that. I am not going to prove this here. They are also forming a vector space. This set of linear functionals also forming a vector space, but they have a different name. If I say this is a vector, sometimes they call this is a co-vector. Co-vector. Also, some technical term are associated with this dual space. That dual space is a homomorphism of the space, vector space with R. So, that means dual space can operate over a vector space. As a result, I am getting a scalar quantity in terms of R. I am not going to that intricacy, mathematical intricacy. Just here my goal is to understand exactly what is going on. So, now the question is very important question, how to represent a co-vector in dual space. For example, say alpha is a vector that I defined in my vector space, and which is alpha 1 E1 plus alpha 2 E2, say alpha n En. This is the representation I want to make. So, this representation is with some basis vector, and this representation in vector space V. So, now the question is what will be the counterpart of these things here. So, which is important? The counterpart looks something like this, alpha. Now, I change this notation. This notation is called Kate notation, and this notation is called bra notation. So, in bra notation what we are doing essentially, I am rotating these things. So, this is now in this direction, I am rotating these things. Not only that, in the right hand side there will be a change. What kind of change will be that? Alpha 1 now became alpha star. If alpha is a real quantity, then alpha 1 and alpha 1 star will be the same thing, but since this is a component of the vector which is a scalar thing, so scalar may be this is coming from the scalar field. So, scalar field may be a real quantity or a complex quantity. So, for the time being we consider a general case that these are complex. If these are complex, I can write it as this. So, it will invert. It will also invert and so on. So, this is the notation of a vector in dual space. So, this is the vector which is in normal space. I am changing the notation and I am saying this is a new notation, and this is not a vector, rather co-vector as I mentioned, but it is a vector element in dual space. So, now if this is the case, now I will going to operate these over that. When I operate these over that, what happened that I will get something which is not a vector quantity, rather scalar quantity. But you should remember that from a say psi, this is a vector in vector space. If I go to its dual space, it will be converted as psi a star. I am going to this vector, I am going to the dual space for corresponding vector, and it will change like this. This things is called dual conjugation. In quantum mechanics, we heavily use these things. You should remember that whenever you are making a dual conjugation, that means you are not in a vector space, you are going to the corresponding dual space. Exactly the same thing I am doing here. I am just rotating this. So, I am rotating this to in dual space, I am making this as this, which is nothing but this, where A is a scalar quantity. Okay, now I define these things and now I operate this over that. When I operate this over that, my things will look like something. So, when I operate that over these and these, so it will be looking like alpha alpha. This is a notation of inner product. So, I am doing the inner product here, it is inner product. I am making an inner product and I am operating this, it is just like this is operating over that. So, if this is the case, then I will operate this entire stuff to here. If I do, then what expression I will expect? I am writing these and these in terms of this. So, in my left hand side, it is alpha 1 star E1 plus alpha 2 star E2 and so on, alpha n star En, this which is this entire thing I will operate over my original vector. Original vector was decomposed with some basis vector like this. So, alpha 1 E1 plus alpha 2 E2 plus alpha n En. So, these multiplied by these will be my inner product, and now term by term I will calculate. So, let us do that here. What will be in my first term? Alpha 1 E1 alpha star 1 E1 alpha 1 E1. So, if I write this alpha 1 star and this quantity gives me mod of alpha 1 square with the term E1 E1. Then if I multiply this to the second term, I will have something alpha 1 star alpha 2 E1 E2. First one, the first term is E1 E1, second term is E1 E2. In the same way, I can find another term which is alpha 2 star alpha 1, which is E2 E1 and so on. and so on. The point is, I have one term which is E1 E1, I have a cross term like this. Also different kind of cross term I find, and not only that, also I find something like alpha 2 star E2 E2, this term and so on. Finally, I will have alpha n star alpha n square mod of alpha n square E n E n. Now, after that I will put some condition over that. So, E1 E2 is chosen in such a way that they are orthonormal to each other. That means E1 EI in general EJ is delta Ij. This is the condition I want to impose. I took the basis in such a way there is a relationship between the basis, and when I apply the relationship to the basis, then I am saying that for this basis this is delta Ij. So, that means they are forming a orthogonality, not orthogonality, it is orthonormal. When one I is I, j is I, then I have 1. So, this property is called orthonormalization. For the time being, just note this term and we will again explain this. So, if I apply this to here, all the cross term will going to vanish. So, essentially what we are getting, left hand side is alpha alpha, right hand side is what, alpha 1 square plus alpha 2 square, this quantity. Now, I know this quantity, this is nothing but the square of the component of the alpha, So, this quantity I can write it as alpha square, this alpha is 2 mod alpha, which is the root over of this quantity is simply called norm the vector, which we know, it is not a very new thing. A vector, if you just realize a vector in just ijk form, what is the norm of that? So, a vector is given in ijk form, the norm is the coefficient square plus coefficient square and root over of that. So, here I am doing the same thing, coefficient square plus coefficient square, whatever the value I am getting, I am making a root over of that, I am getting what is called norm. This is a very important. So, next it is the conjugation of the same vector with the same vector, and this has some properties, this norm has some properties. So, what kind of properties? So, let me discuss right here. This norm has some property. So, first I am defining a vector, then I go to the dual space, then I operate with the inner product notation, then I find a vector, from the vector I am finding some scalar quantity. Now, I am operating the same vector with the same vector, then as a result I am getting something which I call norm. Up to this is fine. Now, what I am doing next is to find out the properties of this. So, you should remember this quantity is always greater than 0. First of all, this is a scalar, no need to explain why it is scalar, because already I have shown that this is the scalar quantity. So, this has to be a scalar. Not only that, this quantity has to be greater or equal to 0, first property. So, norm will always be greater or equal to 0, norm of a vector is always greater than 0. Second property, if it is 0, say I am saying greater equal to 0, so there is a possibility that it will be equal to 0. If this things is equal to 0, then I must say that this vector is a null vector. This vector is a null vector. So, this is the second property. And third property, if I multiply some a with the vector and then try to find out the norm of these things, if I multiply some scalar and with a vector and then try to find out the norm of the vector, then it is essentially the norm of the vector multiplied by the mod of A, which also you can prove very easily. This is the third property we have. Fourth property, which is interesting, that I have alpha plus beta, two vector I add and then try to find out what is the norm of these two vector, which is always following this rule, it is less than equal to individual norm of these two vectors. Now, this is also not a very new thing to you. This is also not a very new thing to you, because this follows simply the triangular inequality. So, how it is following the triangular inequality, let me quickly show, then you will realize exactly what is going on. It is nothing very tough thing to understand at that moment. So, this is my vector alpha and this is say my vector beta with my vector sign. So, if I join that, it will be the vector alpha plus beta. So, what is the norm means? Norm means this length of this side. So, norm means is basically, if I say A, B, C, the norm of alpha plus beta is nothing but AC. The similar way, norm of alpha is nothing but AB and norm of beta is nothing but the length BC. So, from a triangle we know that this always follows AC is always less equal to AB plus BC, which is essentially the fourth rule, So, that means the norms are following certain rules. Sometime there is a name on that, since the norms is following these few rules. If a norm is following these two, if a vector space have a vector element, these vector elements I can calculate the norm of that vector elements with this formalism, and as a result what I am find that some kind of scalar property, and this scalar property, the scalar thing as following these rules, whatever the rules I just show. If they are following that 4 rules, then they are forming a space also, individual space, which is called norm space. So, norm space is nothing but a space where the norm is following that 4 rule. For the time being, you just note that, if you note, it is sufficient. Okay. So, after the calculating the norm, so another thing is important, which is I represent alpha as a, now I am using the summation sign, because now you should be familiar with these things. I am not going to write the entire stuff. So, this summation is nothing but the expansion of these things. I believe all of you are aware of this summation sign. So, alpha I am writing this with a summation sign. I am also writing another beta, another vector beta, which will be defined in a way that beta I E I equal to 1 by n. This is another vector whose components are different, but I am expanding the same vector with the same basis E I and E I. So, now try to find out what is the value of alpha beta. I have already done the calculation for alpha alpha. I am doing the same thing, but just changing another thing, in just changing alpha to beta. So, that means essentially I am doing this. So, what I will do, alpha to n, sorry, this is the notation is changing, this is in Kate notation. Now, I am operating this over B. So, now it is in bra notation. So, bra and Kate I will operate, and this is my the inner product, this is my the inner product. So, when I am changing that, I need to change that also. So, if I change according to the rule, if you remember, it will be alpha star E I. Now, E I will also change, because I am taking the covector multiplied by. summation of I equal to 1 to n and then beta I ei. It will not going to change because I am operating this. You should also note that when this kind of multiplication is there, I can say that for this kind of multiplication, when I conjugate these things, always you should remember that this index you need to change. So, in totality I have ij which is running from 1 to n. If I write this as an index I, so it will be alpha I star, then index j I write bj, and then this will operate with this. So, e I e j, this is the total thing I have after operating that. You should remember that when I multiply, I have already taken care of this issue by changing the index that I already mentioned. So, now what is this quantity? This quantity I already wrote just before, that this is delta ij. If these things are orthonormal to each other, then I can write this is delta ij. If this is delta ij, then my equation is I j alpha I star bj delta ij. If I run now there are two summations, it should be 1 to n, one is over j and one is over I. So, if I have the two summations simultaneously, I can also put another summation sign, but ij, okay, let me put it another summation sign to remove the confusion, that one summation, whenever I do the summation for one I, so it will be equal to 1 when I is equal to j, another case it will not going to be equal. So, if I do the same thing for j, when j is equal to I, then this thing will be 1, another case it will not. So, what value I will eventually get? I will eventually get this value. Alpha I star beta I. This will be my final result, because I am doing the summation. When I am doing the summation, delta ij will be converted to 1 when I is equal to j. So, only these components will be remaining, other component will not be remaining, and I will be ending up with this expression. But the question is, so I have the expression this equal to this multiplied by this, I show that the value I am getting is summation of I equal to 1 to n alpha I star beta I. I am having this. Now, the question is, please take it as a regular basis homework, a homework exercise. Beta alpha, I will just change this ordering. For the first case, I operate alpha over b and I am having some quantity like this. Now, I am rotating these things. I am now taking beta as my co-vector and I am operating this alpha. Also, I am having some kind of scalar. If you do the calculations, you will find these things. So, that means essentially these two things are not same. That means alpha beta is not equal to beta alpha. What is the relationship between alpha beta? This is true only when they are real. If beta and alpha are real quantity, then both the things are same. You should know that. Normally that is the case. A dot b is equal to b dot a only when the components of the vector of a and components of the vector of b are real. If that is not the case, then the actual thing is alpha b is equal to beta alpha with a star. If I make a whole star over there, this star will gone, another star will be there. So, this is equal to this. So, this is the relationship between alpha and beta when they are not the real component, rather they are different components, I mean they are complex components. So, now we understand with the bracket notation what is going on. So, quickly I need to show what is going on in another notation, n tuple notation. So let me do that quickly. So alpha, I can write it as alpha 1 E1 plus alpha 2 E2 plus alpha n En. So in n tuple notation, this is alpha 1 alpha 2 alpha n, this is n by 1 vector. So what happened if I rotate these things? What will be the feature of this notation? So the feature of this notation will be something like this: alpha star, alpha 2 star, alpha n star, it will be 1 by n. So in this is the notation, n tuple notation, when I am making the alpha, when I am taking the alpha as a vector quantity from a vector space. But if when I go to the dual space, something need to be different, and that is whatever the structure I have, which is a column vector, now became a row vector. Not only that, my coefficient has to be there will be a complex conjugate. So the coefficient has to be complex conjugate because of this dual conjugation. You may remember the dual conjugation is, as I mentioned, that when I make a dual conjugation, it will be rotating like this with a star. That means when I go to my dual space, these are the elements sitting here, it has to be star. So this is the case. Now if we exploiting this, if you calculate alpha alpha, which will be the multiplication of this with this, then eventually this is a n 1 cross n vector, this is a n cross 1 vector. So if I multiply these two things, these two matrix, we will have something which is a scalar, and I can write this as mod of the same result that we derived in earlier bracket notation. If you do the same thing for alpha beta, you will getting the similar kind of result. So with that, I would like to conclude. So today we are now learning in a very important process. We are now in a process of learning something very important, which is dual space. And in dual space, we find that the vector can be rotated, and what the formulation will be and how the inner product is constructed. You should know these kind of things in detail. So that's why today's class is important. In the next class, however, we will start from here only, and we will show some example and some elementary example and show how the things is working. So with that, so let me conclude. So see you in the next class. In the next class, we start with this inner product definition, and then we do some kind of problems and show some kind of inequality, important inequality, which is called the Schwarz inequality. How this inequality is working and all these things we will discuss in the next class. So with that, let me conclude today. So see you in the next class, and thank you for your kind attention.